metallization is the back end process, and actually it needs something that to get a circuit. When you employed all the transistor structures, okay, in electrically isolated with the field oxide, but this transistor is going to be connected to form a circuit according to the design, circuit design, and that will be done by this metallization. And I think I will have the metallization. What you do is when you, in terms of the cross section, you have a source and drains like this, and this is a gate, and this is a gate oxide. All right, and then this is separated with other transistors with field oxide, the locus process that we have discussed. And then after this transistor source and another transistor drain or gate or source should be connected to form a circuit. And the way to do this is you just deposit the insulator, and we call this ILD, interlayer dielectric. We call this ILD, okay? And then we form holes, something like this, and this is we call the contact hole. Of course, with the lithography and dry etching process, we make holes, and then the etching should be stopped at each layer, and that layer may be different from one place to another. So you have to be very careful to selecting the dry etching conditions and gases, because you're going to have a different selectivity depending on the substrate materials. So you make a contact holes like this, and then you deposit the metal film all over, and in doing so, this metal has to fill these holes like this, okay? Have to fill up the holes that we made as a contact holes. So you deposit the metals, and then metal has to have a good step coverage. It has to fill up the contact holes. And then you etch this, except the lines that we need for the inner connection to form a circuit. And other metal deposited on top of the interlayer dielectrics should be etched off. We can use the wet etching, we can use the dry etching, but commonly we use wet etching because the metals is very difficult to do the metal etch with a dry etching process. So and the dimensions we are talking about, the metal line width, is not that critical at this stage. Okay, So we usually use the wet etching process for the metal etch and finalize the interconnection of the transistors. And when you make the circuit, you also form a pad. We call this pad. Okay. This pad is for the input and output. This pad is connected to the metal lines that we have formed inside this integrated transistors. And with this pad, after the metallization, we do the passivation. We call that the passivation. We can do this with the polymers, or we can use silicon oxide or silicon nitride, depending on the situation that we have. But we just do the passivation, and with the opening to this input, only this input and output pad is going to be revealed to air, and other areas is going to be all covered with this passivation layer. And then we use a welding, gold wire. We use the gold wire, and we just literally do the welding, okay, to the output plastic packages. And it does have a lead frame. We call this lead frame. Okay. And then when you open the backside of your computer, you can see the chips, and then it has many metal frames, lead frames there. And to that lead frame, we use a gold wire to be connected. Okay, so this is the back end process, and the metallization itself is very important when you first, before you develop the process for the metallization, then you cannot make integrations. With the metallization, development of the metallization technologies, we can have a micro electronic circuit era. Before this, in the connection of the each transistors, we cannot have a integrated transistors. We can have discrete devices, source, drain, and gate, and encapsulated in the epoxy separately. So each transistor is separately manipulated. Okay, but after, it looks like a simple process, but very important. It opens us a microelectronic circuit era. And as you can see here, the metallization is a key process open a microelectronic era. William Shockley, who could not receive a Nobel Prize with John Baden. We have three persons who invented the semiconductors in Bell Lab in 1949, I think. And actually, the Shockley was the leader of that team, but he was staying in England for other researchers. Left his team, three people, John Baden and Seung-ki, and what is that other name? There are three people who got the Nobel Prize. for finding the semiconductors. Okay, and even though the Seung-ki was the leader of that team, he was not at the site of the inventions, so he could not get the Nobel Prize. So he wrote a book saying, I was very frustrated. I was the leader of the team, but my members get the Nobel Prize, but I was excluded because I was in Europe at the time. But the Seung-ki, the next year, he developed the metallization process so that he get the Nobel Prize alone. Okay. So this metallization was developed by the Seung-ki, and the metallization in the connection method in the VLSI, wiring base, this is a pad for input and output, and the technologies we are going to use is a film formation and the lithography, of course. We have to deposit the metal film first, and then we are going to etch them, leaving the wires, very thin wires, using a lithography. Okay, so film formation technologies, we have evaporation, sputtering, CVD, and electroplating, but this electroplating cannot be used in the VLSI because your substrate should be conducting, electrically conducting. But when you do the metallization, everything is covered with the interlayer dielectric, which is an insulator. So you cannot use, except the special cases, you cannot use the electroplating commonly for the metallization. But the evaporation, sputtering, and CVD is commonly used. And among these three, sputtering is the most popular for the metallization. Because the evaporation, it is very difficult to control the thickness. Okay, it is related to the sublimation and things. So in evaporation, you cannot have control, okay, precise control of the thicknesses. And CVD, the operation condition is very strict, depending on the substrate temperature. It is very sensitive. The quality of the metal films is very sensitive to the substrate temperature and pressure and then the gases used. Okay, so this is very difficult, even though it shows a very step coverage, very good step coverage. So the sputtering is the most popular technique to get metallization, and each process has been introduced in this book. And the sputtering, we have seen this. Okay, basically what you do is you have a metal target like aluminum, and then you place your substrate on the bottom, and then you fill up your chamber with the argon, for example, which is an inert gas, but heavy weight molecules. Okay, and then you apply the high voltage to it. Then argon is going to be ionized, argon plus and electrons, to form a plasma around inside the chamber. And then with a self bias, the argon ion is going to hit the metal surface so that the atoms at the surface is going to be sparked off, okay, by this collision. That is a sputtering. And then you can have new thin films. Of course, the sparking rate is not that quick, but anyway, you don't need the thick metal layers for this metallization. The typical thickness that we use is less than 4,000 angstrom. So that is not thick at all, okay? Okay, so the metallization method technique has been listed here. You can just take a look at it and get the reference in it. Metallization, and then we have discussed about this, the step coverage. And the cross section, this is a contact holes. Everything is covered with the silicon oxide and silicon nitride. They're dielectrics, and we call that interlayer dielectric, okay? And then we make a contact holes, and then we try to cover the metals on top of it. And this is the silicon, and then this contact holes, usually this is the area with a heavily doped region, okay? Because this metal lines is going to have an input to the silicon substrate, so that if this is silicon, the contact area is not heavily doped, then we have to have a high resistance. So the portions that we are talking about is here and here. This is the source and drains, and you make holes on top of source and drains. And source and drains is a heavily doped area. So this silicon is a heavily doped region, and then we have a silicide contact. We form a silicide. We are going to talk about why we need that silicide in a minute, but we make a silicide first, and then we have to have a diffusion barrier. And that diffusion is the diffusion from this dopant element, or the silicon itself, to the metals, or the metal aluminum. If you use aluminum, then the aluminum is going to be diffused into this silicon if there is no diffusion barriers. So we use the refractory metals to form this diffusion barrier. Excuse me. And then form aluminum lines like that. So we have this complicated structures, if you look at the cross section there. And we are going to discuss why we need that complicated structure in this lecture, okay? By the way, the silicide is a silicon and transition metal compound. If you if you carry out the heat treatment on the silicon with metals, transition metals especially, then it'll form a silicide. And if you look at the contact carefully, this is a silicon, and then you're going to form aluminum. This is the, let's say, silicon oxide for the interlayer dielectrics, and then you form let's suppose you have aluminum lines like this. Okay, this is a cross section, aluminum lines, and you may see immediately that here the silicon is a semiconductor. It's almost like an insulator, right? And then aluminum is a metal. So this contact cannot be cannot be good, because this is the metal, which is totally different from the insulators, the semiconductors, silicon. The material property is so different. The thermal expansion coefficient, or the toughness, or the hardness, and everything, the material properties are so much different, so that the contact between these two cannot be good, right? So the silicide is nothing but the materials in between the metal and the semiconductors. So the silicide has a properties in any sense, some of the metal characteristic and some of the semiconductor characteristics. So it's an intermediate materials. Okay, in terms of the resistivity, is in the silicide resistivity has to be in between these two, and thermal expansion coefficients and everything. So if you form a silicide before you put the aluminum metal on top, then the adhesion can be improved. Okay, that's why we form a silicide. The desired properties of the silicide: low resistivity, of course. If it has a high resistivity, then the contact of the metal to the silicon is not going to be good. It's going to be blocked by high resistance material. So, firstly, it should have low resistivity, easy to form. If it is difficult to form, then what's the use? Okay, easy to etch and stable in the oxidizing ambient, because the silicide is going to be formed on the silicon. It should be immune to the environmental conditions like oxidizing ambient, mechanical stabilities, surface smoothness, yeah. No reaction with the final metals, also important. If it form an intermediate compounds in between here, then you're in trouble. Okay.